Hi, I'm Kenneth Sampson, and you are currently watching a video from the MII Senior Expo Take a Strand. We had the opportunity and privilege of inviting speakers to speak on their field of expertise and to educate us on their profession and how we can relate it to our strands and also to our daily lives, as well as to assist students if a career, field, or strand is right for them. Now, without further ado, we hope that you learn from the video.
So, welcome to the first MI Expo Take a Strand. It is my pleasure to welcome our guest speaker for today, Dr. Ryan Llorin. He's an infectious disease specialist. He has a diploma in infectious diseases at Tan Tock Seng Hospital and St. Luke's Medical Center, a certificate in travel health and fellowship. Dr. Llorin will be representing the science, technology, engineering, and math strand by speaking on vaccines and inoculation. Again, let's give a warm round of applause and a warm welcome to Dr. Llorin.
So thank you. Thank you for that nice introduction. I'd like to share a slide, if I'm able to see. Let me start my talk. So yeah, thank you again for inviting me. I just learned that my son Erin is in another breakout room. So anyway, I'll be talking about COVID-19 vaccines. So this is the topic that was given to me by your class. Okay, so see, see. So these are my objectives. So essentially, at the end of this session, what I want you to learn is number one, understand how vaccines protect us from infections, and learn how vaccines are made and how they are introduced into the general population. Okay, give you an overview of the COVID-19 vaccines that are currently out there in the general public, and allow me to show you how to know, no, if the vaccines are effective. Okay, so before going into the vaccines themselves, it's important for us to understand the basic concepts of our immune system. Okay, so I'm sure you've had a relative, or maybe one of you had an unfortunate uh, circumstances of getting sick, and you know that sickness, especially in terms of infectious diseases, are caused by germs in the form of a virus, bacteria, a fungus, or maybe a combination of these, right? And in order to fight off these germs, we need medications. No? It could be in a tablet, it's an intravenous form. You probably had an opportunity to stay in the hospital and get lots of medications. But ultimately, it's not the medications that will actually decide, the outcome of a particular illness. The medications are there to help, you know, our body fight off the infections. But in the end, it's actually our immune system that will be able to eradicate, and will determine the outcome if you have such an infection. So let's now go to our immune system. So there are two general subcategories of your immune system. No? If you want to put it simply, first you have the innate response, or you have your adaptive response. So you can also call this as the innate immune system, and the adaptive is the adaptive immune system. So in this diagram, let's use the SARS-CoV-2 as the germ, as the invader of our body. So a COVID virus, the SARS-CoV-2 virus, for example, once it enters into our system, is encountered by our the first line of defense, in the immune cells. there are different kinds of immune cells, but the first sign of defense would be molecules or substances or cells in the form of natural killer cells. Okay, this is your innate response. Okay, this response would come in a matter of minutes and hours, because it's important to fight off, recognize the presence of a foreign body and fight off the infection. Okay, but these molecules, the innate response is not adequate enough to kill a virus or a bacteria. It requires a stronger immune system, which is your adaptive immune system, to be able to eradicate and kill viruses. So your adaptive immune response takes a while to go into action, but it is a more specific and a stronger component of your immune system. So if you look at the diagram below, you see there's a timeline, right? So your innate response goes into action in a matter of minutes to day, but while your adaptive response takes a while. It takes about days, just a few days. And your adaptive response could consist of your macrophages, your B cells, your T cells, your plasma cells, and your antibodies. And your vaccines are actually acting on your adaptive response. Okay, the vaccines that you get will stimulate the adaptive immune system to fight back. Okay, so the vaccines are actually, and these are medications that we give to our patients to stimulate the immune response to prevent infections from getting hold of our body. Instead of waiting for the immune system, for the infections to do its damage, our vaccines are there to go into action and prevent. That's the important word. The vaccines are there to prevent infections from getting worse. Okay, so let's go more specifically into the adaptive immune system. So first of all, when you have a foreign body in a form of a germ, or let's say, for example, let's talk about the COVID virus again. Once it enters your system, your immune system is alerted to the presence of a particular invader or a virus. So the first one that gets activated with your macrophage. Your macrophage will ingest some of these germs. They will process these germs, and then they will present a subunit or a viral component of this virus on its outer surface. So you can see here, you see the teal colored macrophage. It has an arm and showing a small pink circular component. That pink circle is a subunit of the virus. It's presenting the component of the virus outside its surface, and the reason for that is it's actually calling on the rest of the immune system, alerting the rest of the immune cells to the presence of an invader. Okay, so the next cell that gets activated would be your helper T cells. Your helper T cells is another component of your immune system. Its role is actually to wake up the rest of the immune cells. Okay, so the helper T cells, for example, will call on your B cells. Okay, the B cells, these are the non-specific lymphocytes that eventually will form into plasma cells or your memory cells. The plasma cells here will produce the antibodies. Okay, the antibodies, these are proteins that will eventually attach to the circulating pathogens, or in this case, the virus. All the viruses that are circulating in your system will be recognized by the antibodies. So the antibodies will attach to this virus, okay, making it easier for the rest of the immune system to recognize this particular virus. So you look at the antibodies as it's like a red flag. You know? So imagine going around the field with a red flag, that it's easier for you to be recognized by everyone else. So once the virus is already surrounded by your antibodies, okay, the other component of your immune system, which are your cytotoxic T cells, your cytotoxic T cells will now be able to recognize the germs, the virus, and it is the role of your cytotoxic T cells to kill these viruses. Okay, the cytotoxic T cells will kill these viruses that have been marked by your antibodies. Eventually, of course, the virus or the bacteria die, and then you recover from the infection. But the work of your immune system doesn't stop there. You remember your B cells, which eventually becomes your plasma cells. Some of your B cells and your plasma cells eventually will turn into memory cells. So memory cells are another component of your immune system. Essentially, these are B cells that have been converted into a specific type of cells whose job is actually to remember the particular virus or bacteria that your body has encountered. So it's important to have memory cells, because next time when you get another infection by the same pathogen, by the same virus, or by the same bacteria, so your memory cells will go into action immediately. It doesn't have to wait for several days. The memory cells will say, oh, I recognize this bacteria, I recognize this virus, so I will immediately go into action and try to kill this virus. So instead of taking a few days for your immune system to wake up, it will only take a few minutes or a few hours, thereby preventing the germ, you know, from setting foot and causing an infection. Okay, so where does a vaccine come in? Essentially, your vaccines, they mimic the germs. Okay, the germs are your germ. The vaccines are your germ impostors. So meaning, instead of waiting for the virus to come in and stimulate the immune system, the vaccines themselves will pretend to be a germ and stimulate your immune system. So what's the advantage of having a vaccine then? So aside from stimulating the immune system, you avoid the bad consequences of actually having the disease, right? You are able to develop a protection without going into the whole process of having the disease. Okay, so you don't have to have, let's say, for example, you don't have to have mumps, you don't have to have chicken pox, you don't have to have measles to develop immunity. The vaccines afford us to have that specific protection without actually suffering from the disease. Okay, when a vaccine stimulates the immune system, you call that the primary response. Okay, that takes a while to develop, just like in a real disease. That's why sometimes you hear, right? For example, you need multiple doses of a vaccine before you get complete protection, right? So in the case of, let's say, COVID, you have to get 2 doses for certain vaccines, and you're not even completely protected after 2 doses. You have to wait for another 2 weeks before you can say you are completely protected against COVID. So the reason for that is because it's the primary response takes time to develop. Okay, so then comes the secondary response. What's the secondary response? When the actual pathogen, when you encounter the actual virus, okay, your immune system is already familiar with this particular virus because of your vaccine. So what's different from your secondary response? It's faster because your immune system is already able to recognize, and it is just as strong. Okay? It is able to develop millions of antibodies. So enough antibodies, enough killer cells, your killer T cells, to overcome a virus. So that's that's the advantage of getting the vaccine. Okay, you avoid the bad consequences of the disease. You have a faster response, and you have a just as strong immune response as when you get, just like when you get a real infection. Okay, so now let's talk about how vaccines are made. So vaccines actually, the process of making vaccines is actually quite complex. Okay? But we have come a long way since the development or the discovery of the vaccines. So maybe can any one of you guess when was the first vaccine introduced or used in a person? Okay, so you think about that. Yeah? So yes, this is the process of uh, developing a vaccine. So essentially, a vaccine, as I said, is a germ imposter. Okay, and its job is actually to stimulate the immune system. But the component of the vaccine or a virus that stimulates the immune system, you call that the antigen. Okay? The antigen, that's the protein that actually tells your immune system to develop antibodies or to develop killer T cells. So in the process of making a vaccine, first you have to, of course, get the pathogen, get the virus. You should be able to grow the virus and then harvest this virus so that you are able to get the antigen. So in most cases, we use certain cells. In the case of your virus, they use chicken embryo cells to grow the virus. Okay. Once you've grown the virus, you need that particular component. You don't need the whole virus in most cases. You need only a portion of that virus, which you need to get, and you need to release it and isolate it from the medium from which you have grown the virus. So that's the second step, separating the antigen from the medium. And after that, of course, you need to purify the antigen. So you don't want to actually, give a vaccine that contains the real virus, because the host may eventually develop the disease rather than just the protection. So purify the antigen, and they use processes such as chromatography or ultrafiltration. But essentially, this is just separating and making it into a purer form. So after you have purified the antigen, you now prepare it to make it a stronger substance. So we add adjuvants, stabilizers, and preservatives. So the purpose of the adjuvant is a substance that it enhances the immune response. Okay, the stabilizers will make the vaccine stable. Okay, it won't get destroyed easily by, let's say, by temperature, by heat. Okay, and preservatives allow you to give multiple doses of vaccine in a vial instead of one vial per vaccine. So all these components, you combine them together, and then you come up with a very strong, stable vaccine, right? Go. So now you have a strong vaccine. That's ready for administration. So you mix it, you pack it, and you get ready for delivery. So now we have a vaccine. So now we can give it now to your patients. But okay, stop. Okay, we don't just give a vaccine without actually checking whether it's effective, whether it's safe. So the next step is what we call the clinical, preclinical and clinical phases of preparing the vaccine for administration. So essentially, there are 5 steps of studying whether this vaccine is effective, whether this is safe. So the first phase, we call it the preclinical. Clinical, when you say clinical, it's you study human beings, okay? But in this case, in preclinical, you study animal subjects. So the purpose in the preclinical study is to determine what's the appropriate dose, what's the right formulation, whether can you give it in a tablet or can you give it in an intravenous form. Okay. Yeah, during this phase, you also want to know what the vaccine does to the body and what the body does to the vaccine. So it's all studying about we call it the pharmacodynamics and then the pharmacokinetics. So what's going on in our body and how our body processes the vaccine. Okay, so during the next phase is phase 1. Okay, in this case, you use a small number of healthy people, and you try to assess the vaccine safety. Okay, you try to assess if you are able to induce an immune response, and you look for, and to a certain extent, you would also look for some side effects. So after you have passed that stage, you now go into phase 2. In phase 2, it's much like phase 1, but in this stage, you use a bigger number of people and more diverse group of subjects. So still healthy subjects, maybe different age, some form of mild diseases, okay? But definitely these are a diverse, different group of subjects with different characteristics. And during this phase, you also want to determine the schedule of giving the vaccine. Whether can you just give it once, can you give it twice, can you give it every 4 weeks, 2 weeks, or every 8 weeks, right? So then you have your phase 3. So phase 3 is giving it to thousands of people. This time you definitely have a more diverse group of subjects, and you give it under general, under usually natural disease conditions. So in this phase, patients may already have some form of a disease. Okay, so let's say in COVID, you have somebody who's had COVID before, was no COVID, and then you look at what happens after getting the vaccine. Will they develop COVID disease or not? Okay, so once it has been approved, no, that in this case it has to be approved by the FDA. That's when you introduce it now to the general population. Okay, this is what you hear or what you read in the newspapers when the healthcare workers are already getting their COVID vaccine. So what we do here is we collect data on the vaccine usage, adverse effects that we haven't seen during the clinical trials. And because this is already out in the public, you can now look at the long-term effects and the long-term immunity. But overall, all throughout these phases, you test for the immunogenicity, for the safety, and the adverse effects caused by the vaccine. So that's the most important thing. Okay. So now let's have an overview of the COVID-19 vaccine. Okay. So there are 3 main types of COVID-19 vaccine. depending on how the vaccine is prepared. Okay, so the first one is a whole virus vaccine. The second one is a parts of a virus vaccine. Okay, and then the third one is a genetic material of a virus. Okay, so what's common to these types of vaccine is the immunogenicity, meaning all these types of vaccine has the ability to stimulate the immune system to produce the antibodies. Okay, let's go through this vaccine types one by one. Okay. Okay, so this is for the whole virus vaccine. So there are actually three types: the inactivated virus, the live attenuated virus, and the viral vector vaccine. When you say inactivated virus, it contains the whole virus, but in this case, you have already killed the virus, but you kill it in such a way that you don't render it useless. You don't make it unable to stimulate the immune system. It's been killed in a form of by the form of chemicals, heat, or radiation. Okay, but it's still a killed virus can stimulate the immune system. Okay? So this is how we develop vaccines during the early years. So it requires special laboratory equipment. It requires prolonged production time, and in most cases, you would need multiple doses of vaccine injection, okay, for to have complete protection. Okay, so during this time, an inactivated virus may not be very very helpful if it will take a long time to produce the virus. So the next one is a live attenuated virus. In this case, the virus is live. It's alive. However, it has been weakened. You know, it's weakened in such a way that it's not strong enough to actually cause an infection. However, a live attenuated virus should never be given in patients who has immunocompromised immune system. You know, who has a compromised immune system. Because if you have a weak immune system, okay, the live attenuated virus can actually become a real disease. So live attenuated virus, these are the types of vaccines that we don't give for pregnant women, patients who, let's say, for example, has cancer, who are undergoing chemotherapy, patients who have undergone bone marrow transplant. They are not allowed to get live attenuated virus. Example of your live attenuated virus would be viruses you use for chickenpox, measles, mumps, okay, rubella. Another whole unit vaccine is your viral vector vaccine. So this one is quite interesting because actually you have two viruses. One virus will serve as a vessel, and the other virus will serve as the actual vaccine. So that virus, let's say your COVID vaccine, right, it's placed inside another virus, but this virus is actually safe. No? It will not cause the disease, but this virus will just it enables you to enter the system without, and then also stimulate the immune response without actually be destroying the actual virus or the actual component inside. Okay, so this is an example of how an inactivated coronavirus vaccine works. So you have an inactivated coronavirus vaccine. Okay, so you introduce it into the system. Let's say, for example, in the form of injection. It enters your system and it encounters your macrophage. In this case, your macrophage is also known as an antigen presenting cells. It's called antigen presenting cells because then when the macrophage ingests the virus, the vaccine, okay, for example, it processes that vaccine and it presents the antigen on its outer surface. When it presents the antigen on the outer surface, it activates the helper T cells. Once your helper T cell gets activated, you know what happens, right? We've talked about that earlier. Okay. So the next vaccine is a parts of a component. It's a part of a virus. This one, you just need a specific part, a subunit of the virus of a or a bacteria. You don't need the whole virus. Okay. So let's say you look at the COVID virus. Your COVID virus is actually a very simple virus. It's composed of just a few proteins. So you have this shell, the lipid, the overall coating, we call it the lipid membrane. And on the lipid membrane, you have certain structures. On the surface, you have the spike protein, and embedded in between are your envelope protein, and then you have your membrane protein. Inside this shell is the nucleocapsid protein. Okay, the nucleocapsid containing genetic material, okay, telling the virus how to, it's like the brain of the virus. But in this case, if you have a parts of a virus vaccine, you only need a certain part of the virus. You don't need the whole vaccine. Sorry, the whole virus. So in most COVID-19 vaccines, you only need the spike protein. Okay. What's so special about the spike protein? Because the spike protein, that's the part of the virus that the virus uses to enter and invade a cell. Okay, the first interaction between a virus and a cell is, of course, attachment. So they use the spike protein to attach into a cell. So if you want to stop the first step, and the way to stop the whole process is you target the first step, and that's the attachment. So that's why you want to develop antibodies against the spike protein. Okay, so the last type of a virus vaccine is the usage of your genetic material. So, okay, your genetic material, it's like a code, right? Sorry. So the genetic material is like a code. It contains instructions, no? It tells the body to produce, the cells. It produces proteins, sugars, your carbohydrates. Okay, so in terms of vaccinology, this genetic material tells the body, this particular cell, to produce a subunit of the virus. In this case, the spike protein. So if you look at the diagram, you have the genetic material inside the vaccine. So this genetic material is exposed once it enters the system. So your body picks up the genetic material, and then you have the ribosome. So it's like the factory. The ribosome reads the instructions, and eventually it tells the cell to produce a protein. So in this case, it's a SARS-CoV-2 protein. So this protein is being produced, and this is picked up by your immune system. Okay, your immune system will now develop antibodies against this viral protein. And over time, you have your immune system reacts to this viral protein, and then you have your memory cells, you have your plasma cells. It remembers the COVID virus eventually. Okay, so this is what we call the mRNA vaccine, because the genetic material is the mRNA. So it's a new method to produce vaccines. It's quite safe. You can develop it very fast. In fact, you can actually manipulate the vaccine, because you can put there what kind of genetic material, and then which eventually tells the body, that it gives the body the instructions. So it's easy to design, it's easy to produce, and easy to test. So now let's go into the actual vaccine. So what COVID-19 vaccines are available? Okay, so there are actually hundreds of vaccines that are in development. But when we talk about vaccines that have reached the phase, starting from phase 1 to phase 4, there are only a dozen vaccines. Why do we have so many vaccines in development? because we want to, that increases our chance. Okay, that increases our chance of developing a successful vaccine against COVID-19. Okay, so currently there are about 13 vaccines that have been authorized for use in the public. Okay, these are uh, these are the 13 vaccines that are used in the general population worldwide. I'm sure you're familiar with a few of them, but let's talk about vaccines that are here in the country. So the first one is your uh, Sinovac. So Sinovac is actually the company that produces the vaccine. The name of the vaccine is the CoronaVac. So what kind of vaccine it is? It is an inactivated virus vaccine, meaning you have the whole virus inside the vaccine, but it's been killed. It's been inactivated. So the efficacy depends on which study you're looking at. So they did a study in Brazil, it's about 50%. In Turkey, it's about 90%. The reason for this is because the study design was the study designs were different. Okay, so Sinovac, you give it 2 doses, 2 weeks apart. No, okay. So for us in the medical field, we have received our Sinovac vaccine. So I've received my second dose the other day. Okay, so I didn't get any side effects, so thankfully. Okay, so the next vaccine is your AstraZeneca University of Oxford vaccine. So this is the second vaccine that's available in the country. So this is your viral vector. So okay, the vector is the adenovirus. The adenovirus, inside the adenovirus is your COVID virus vaccine. Okay, so you give it 4 months apart. The efficacy is about 79%. But recently, the AstraZeneca vaccine is quite controversial because there is a concern that it causes blood clots in the young population. So currently, trials on children are suspended. Okay. So that other famous vaccine that we have, but it's not here yet in the country. We have the Pfizer Biotech COVID-19 vaccine. So this is a vaccine that uses the new technology. This is the mRNA vaccine. You give it 2 doses apart. The 2 doses, 3 weeks apart. The efficacy is about 95%. Side effects include fatigue, fever, and muscle aches, but these are just minor, and it has found to be effective in the young adolescents. Okay, so the other one is the Moderna vaccine. Okay, so this one is 2 doses, 4 weeks apart. The efficacy is about 94%. The advantage of your Moderna vaccine over their Pfizer vaccine is that you can keep it in the room temperature, whereas in the Pfizer vaccine, you really require sub-zero temperature to keep it viable. So there are ongoing trials for adolescents, young children, and babies for the Moderna COVID-19 vaccine. Okay. So now this is the last part of my talk. So we want to know, how do we know if the vaccines are effective? So the first one, during the clinical trials, phase 1, phase 2, phase 3, we measure the antibodies. You get the vaccine, and then we collect blood, and we try to find out if the subjects eventually develop antibodies. But the antibodies are surrogate markers of infection. We want real world data. We want to know whether do you develop COVID-19 or not, right? So this is a phase 2 trial, a phase 3 trial looking at the Pfizer BioNTech study. So there are 2 lines, right? The blue one and then the red one. So the blue line represents the population who did not receive the vaccine. Okay, the red line represents the population who received the vaccine. So it actually measures the incidence of COVID-19 cases. So as you can see, there are higher COVID-19 cases among those who did not receive the vaccine compared to those who actually received the vaccine. So I think this is in the rate of like, you see, less than 0.4%, whereas compared to those who received the vaccine, about 2.2% develop COVID-19. So you might say that these are just small numbers, but here for us in the medical field, the difference is clinically significant. Okay, it is clinically significant that we consider the Pfizer BioNTech as a protective vaccine. Okay, so another way to find out whether the vaccine is effective is we look at the cases in the population. So this is the number of COVID-19 vaccines that have been administered in the United States. So they first introduced the vaccine back in December. So now they are actually giving it like 3 million injections per day in the US. Okay, so what happened to the COVID cases in the US? So in terms of the number of cases, this is the first part, the uppermost part of this slide. In terms of cases, you see a drop in the number of COVID cases. How about deaths? Okay, there's also a significant drop in the deaths due to COVID-19. Okay, and it also, of course, in terms of hospitalization, there is also a drop in the number of people who were hospitalized to COVID-19. Why are we looking at deaths and hospitalization? Because in the real world, what matters to us is for the vaccine to prevent you from getting severe illness. This is represented by the hospitalized cases, and prevent you from dying because of COVID. So you have the incidence rate of deaths and hospitalization. The vaccine will not be very helpful if it only prevents you from getting mild cases, but it doesn't prevent you from dying or getting a severe illness. So clinically, it's very important. It's not good enough that you just have a vaccine. You want a vaccine that has a real impact. Okay, you want a vaccine that actually prevents you from dying. So these are the parameters that we are measuring. Okay, so let's look at the what happened to the population in the nursing home. During the early part of the pandemic, thousands of elderly died in the nursing home, okay, because of COVID-19. So as you can see here, right, following the introduction of the Pfizer vaccine, you see there's a drop in the number of COVID cases in the nursing home, and new cases in the nursing home. Okay, and then if you look at the deaths, okay, as you can see, more deaths were prevented after the introduction of COVID vaccine. So much so that the deaths in the nursing home were much lower compared to the general population. Okay, so okay, this is the current status of the number of COVID vaccines that have been administered worldwide. Of course, number one is US, followed by I think Chile. There's Israel, and then certain parts of there's UK. Okay, in the Philippines so far, 2 days ago, we have less than 1 million Filipinos who have received the vaccine, and that's still not enough. You have only about 0.7 per 100 people. Okay, yeah. So that's my last slide. So thank you.
Thank you, Dr. Llorin, for that very eye-opening and informative presentation. I'm sure that the students here today were able to learn a lot from your lecture. We'll be allotting this time for a Q&A session, so feel free to type down your questions in the chat box. You may also opt to send your questions privately to any of our hosts if you wish to ask anonymously. All right, we have a question. Okay, we have a question from the chat box. For the Astra vaccine, if one of the effects is blood clots, can they medicate themselves with blood thinners when they get vaccinated?
Um, that's a good measure, but as much as possible, we want to actually prevent getting complications from the vaccine because number one, uh, medications that will prevent blood clotting will also have its own side effects, right? You might get bleeding from the medication, and use of these medications would require monitoring, laboratory monitoring. So that's an added cost. So as much as possible, we want a vaccine that's also safe and not just effective. Okay. So you also don't want to take the risk of having a severe bleeding after a vaccine.
Oh, we have a lot of different questions here, Dr. Llorin. If you can open the chat, I think you can just choose whichever ones you
Okay.
want to answer, if that's okay.
Okay, let me. Okay. What if people are scared to take the vaccine? So you mean they're scared of taking the vaccine? So I think we have to do our part to educate people. So there are those who doesn't believe on the vaccine, who are scared of the vaccine side effects. But ultimately, hopefully, everybody gets the vaccine because it's not just to protect yourself, but you also protect your family. Okay, you also protect your classmates. By getting the vaccine, you prevent the virus from persisting in the community. You prevent the virus from transmitting it from one person to another. So imagine, let's say, in your community, in your class, if let's say you are 50, 45 decides to get the vaccine, and 5 did not get the vaccine. So there's still a chance that the virus will enter your community, right? So because 5 did not get the vaccine. But the virus will not just stay within your class. The virus will also go into your uh, households, into your own homes. And we have some patients who are also unable to get the vaccine because of reasons like allergy. So, or maybe because they haven't had the opportunity yet. So you may have your grandmother or your grandfather who's just there lying in your bed. They don't have the vaccine, and you are, if you unfortunately brought the vaccine home. Okay, so that's the reason why it's important for us to understand that ultimately the vaccines are very beneficial, they're very helpful. You may have some side effects, but these side effects are just minor.
Now we have another question here. Is there a specific health criterion to meet when administering a vaccine, like cell count, oxygen level, etc.?
No, as long as you are healthy, you're not showing any signs of sickness. You're not showing any signs of COVID flu-like illness. It's safe to get the vaccine. The only contraindication would be a history of severe allergy to the vaccine or any components of the vaccine. But as a precaution, if you are sick, you better see the doctor first before you get the vaccine.
And there's
We
a
got an
question.
interesting one actually here. It says, hello, sir. FDA just allowed Sinovac for seniors after announcing it is not advisable for them last week. Why the sudden change? What made it suddenly safe for seniors?
Okay. If you look at the trials, the trials usually is the purpose of the clinical trials is to look at the effectivity and the safety. Okay. During the trials, you want to give the vaccine, you want to know whether it's effective, but at the same time, you don't want to put people at risk. So that's why they limited the study to a certain age group, I think between 18 to 59, looking at the different trials, mostly 18 to 59. So when they found out that the vaccines are working, that's the first criteria. You have to give it only between 18 to 59. So they excluded the elderly. But ultimately, because of the seriousness, the gravity of the pandemic, we think there's no biological basis of excluding the elderly population. No? There's only a difference in age, but as far as side effects are concerned, it's not a very big deal. So you weigh the benefit and the risk. No? So if you have it would be more beneficial to vaccinate the elderly population, then definitely go for the vaccine. So currently we don't see any. We've had doctors who are more than 60 years old who were brave enough to get the vaccine despite the limited criteria, and so far they're quite well. And if you look at the US study, remember, they gave the vaccine to elderly population, even if the clinical trials say they limited it to below 60. And then look at what happened to the COVID cases in the nursing home. Okay, it dropped. Yeah.
Now I have another question. So for students who want to be doctors, what made you choose your specialization? And will the demand for your field increase due to the pandemic?
Yeah. So why did I choose infectious disease? I think if you, because infectious disease, it takes a lot of it's like you're a policeman. You investigate. Doctors do not, the patients do not come to you and tell you you have dengue, you have pneumonia. They don't know what they have. So it's up to you to investigate. Okay, so that's the part that interested me in infectious diseases. So will there be an increase in infectious diseases specialty? Yes, there will be, because remember when we had the first SARS virus. Remember SARS back in 2000? I don't know, when you were still very young. There was there's a SARS-CoV-1, which is back in 2003, and soon after that pandemic, everybody was saying it's only a matter of time before we get another pandemic. So they're actually saying the same thing. It's only a matter of time before we get another virus that will cause another serious pandemic. So we see, we call it the emerging diseases. So this is how we envision the future. Unfortunately, so more pandemics to deal with, to take care of. So we really need more doctors to help us with to battle the disease. Yeah.
Unfortunately, we only have time for one more question, so this will be the last one for today. So what are the difficulties you have faced with working in an environment that's even more susceptible to the disease?
What are the difficulties of? Okay. I guess the difficulties that we are facing right now is, well, for you who are the people that we serve, the patients, we don't have enough bed space. We don't have enough facilities to bring in all the patients who are sick, unfortunately. So you have to tell, that's my message to you and to your family and to your friends. You have to maintain, follow the quarantine protocols so that we can prevent this disease from spreading. Okay, so that we can put it under control. So that's one difficulty. The other difficulty is that all the doctors, the nurses, they're already tired right now. It's been 1 year since the pandemic, and we haven't had like even a break, no? It's quite difficult going inside the hospital. You see a lot of patients who are suffering, right? These things that you don't see in the news. Then the other thing, of course, is Of course, everybody's scared of getting the virus among us healthcare workers and bring it to our family at home. Okay, so we always do our best to follow the protocol, to always clean our hands, wear our mask and our face shield, make sure we also protect ourselves. Yeah, but it's okay, it's fun.
All right, thank you. Once again, we'd like to take this chance to show our gratitude to Dr. Ryan Llorin for sharing with us his invaluable time and for being a guest speaker in our very first MI Online Expo, Take a Strand. Let's give him our virtual applause using the reaction button.
Before you go, please make sure to answer the feedback form that is located down below on the description. Aside from that, we would like to thank our sponsors as well, White Breeze Palawan Hotel, Food Talk Supermart, and the Regalado family for their help. Once again, thank you for your participation. Signing out, Batch of 2021.